the higher atomic number elements have shorter lifetimes. Yeah, so the greater you get a greater broadening, and this gets to be a limitation for high GH. So once your energy is higher, then you will get a more broadening spectrum. And although it can be deconvolute out in a favorable case, but when the high G elements, and your spectrum will become more broader. But for atomic number, that means a low G element, low atomic number. And we can name this spectrum as near edge X-ray absorption fine structure. And for low G element spectrum, because uncertainty principle, so you know that you can get a sharp spectrum line. And with such sharp spectrum line, you can analyze the spectrum much well, and you can know more detailed information. But your spectrum is very broad, and it will have difficult to interpret this. And the other ways to using the new techniques is X-ray inelastic scattering. And this technique can be used to suppress cohort lifetime broadening and explore X-ray absorption near edge detail. And I think nowadays in some new generation synchrotron source, like Sprint A, APS, or ESRF, and you can do in such kind of X-ray inelastic scattering. And you can also measure the X-ray absorption spectroscopy. Then you can find your spectrum. For example, your pre-edge will be more sharp than general measurement. Okay, let's review it. Please remember the final state symmetry. For KH, it's for KH at the beginning, 1s initial state, n equal to 1, L equal to 0, m equal to 0. And for L1H, the initial state is 2s, n equal to 2, L equal to 0, m equal to 0. And according to the dipole selection rule, project out specific symmetry component. The final state wave function should be K and the L1H, the proper P part of the final state. And for L2 and L3, your initial state is n equal to 2 and L equal to 1. So the selection rule, dipole selection rule, tell you delta L must be plus or minus 1. So that means the transition from 2p will be will to D state or S state. That means that you can probe the D part of final states. Okay, now let's look at these figures. For horizontal, your instant photon energy. Here we use the KeV, and here is the absorbance. And this is an example of LED, PB. And if you increase your photon energy from 1 keV to up to close to 1000 keV, you can find a spectrum wheel like this. At the beginning, the intensity will go down, but to certain energy will go up, and then will go down with increasing of your energy. The absorbance will go down again, and with certain energy, it will go up and then go down again with increasing your photon energy. Then above 100 keV, the intensity will go up again, and then with increasing your instant energy, the absorbance will go down. Okay, so you can find this, there's some H appear when you tune in your instant photon from 1 keV to 1000 keV. You can find such feature. So that's why we call it a KH, LH, and MH. If you zoom out this region, actually you can find is the more detail. So you can find between 10 to 20 keV. You have not only you have L3, L2, and L1. So this means just want to show you if you have you increase your photon energy from 1 keV to 1000 keV, you can probe this element Pb, and it's Kh, LH, and Mh. For each element, actually, because each element you have 1s, electronic configuration, you from 1s to 2s, and you can excite for hydrogen. You already know. You only have 1s electron, and for helium you have two 1s electron. For lithium, your electronic configuration is 1s2 and 2s1. So for each element, you can excite its 1s electron or 2s or 2p, and then the energy is different. So you can find such kind of table in internet or any public site, and that means you can tune in your instant photon to knock out the electron from K level or L level or M level, and there will be quite different. For example, here, manganese is 1s orbital. Its Kh is around 6,500 electron volt, and for the iron, its Kh is about 7,100 electron volt. So that you can consider there's about 600 electron volt difference. So if once you have a material, you include manganese and iron, actually you can distinguish these two spectrum. Okay. Now we will go to discuss about X-ray absorption spectroscopy. And remember this, this is a general feature of X-ray absorption spectroscopy spectrum. And for this case, actually this is copper. No, sorry, this is a zinc element. Actually, because you have this table, you can remember this. For zinc, the 1s the Kh is about 9,600 electron volt. So when we see such spectrum, we already understand you will excite this zinc element. So and you excite the 1s electron, and you obtain such a spectrum. And we consider this this region here in the purple one. This is an X-ray absorption near edge structure. And that means we see increasing your energy above edge and up to 30 or 40 electron volt. We consider this region as X-ray absorption near edge structure. And after this, you can go up to 1,000 electron volt, and we consider this region is an extended X-ray absorption fine structure. And in this region, you can find such oscillation feature. And you can consider such oscillation feature like you have a absorbing atom, and the knockout electron will give out an outgoing wave, and you have a neighboring atom will backscattering this wave. And you consider these two waves will interference. And for here, the green means that you have in-phase interference. So you obtain constructive. And for red, here you can find it's a destructive interference. Okay, now let's look at this one real example. And here is a manganese oxide oxidation state. Well, the energy, the manganese Kh about 6,500 electron volt. And you can see for the green one compound, at the beginning, for this compound, you have two manganese. These two manganese is both are manganese 2 plus. And you can oxidize it. And if you have one manganese be oxidized, then when you go from 2 plus go to 3 plus, and you find this the red line, the absorption spectrum, now it becomes a red line. And there's one manganese be oxidized from 2 plus go to 3 plus. And if two manganese both be oxidized, and then you obtain the blue line. And if further oxidize one manganese go to 4 plus, you obtain this pink one. So one interesting is if you comparing these 4 spectrum, this rising edge region, you can find that for the higher oxidation state, this you have 1 3 plus, 1 4 plus. The blue one is 3 3 plus, and the red one is 1 2 plus, 1 3 plus, and the green one is both 2 plus. And you find when the oxidation state go to higher, the rising edge also shift to higher. So that means you can distinguish these 4 states based on the rising edge. Now let's move to another example. This one, you have a compound. This is also a manganese, and you have a manganese, and this 4, and you have a manganese. You have manganese bonded to oxygen, and this comparing to another case is manganese 3. And you have one is a green line spectrum, the other one is a blue line. If we enlarge this region in this insect figure, the green line, you can find it's shift to higher energy comparing to the blue one. Okay, so you understand the oxidation state of green one is higher than the blue one. And another case is here. Here you have for the green one, the pH, this intensity is higher than blue one. And why? If we consider the electronic configuration, the neutral manganese is 3D54S2. And when it becomes the 4 plus, the electronic configuration, it becomes D3. So you have 7 unoccupied hole. And for the manganese 3 plus, it's D4. So you still have 6 unoccupied state. And we already mentioned you transition from occupied to unoccupied state. So once you have more unoccupied state, your intensity will become higher. So this in this quite often we interpret this 1s to ND state, 1s to 3D state. So if you have more unoccupied D state, your intensity will be higher.